Good morning.
Good morning. Thanks for so energetic. Yay. Just letting everyone in, so give me a sec, everyone.
Yo, yo, yo.
Hey, hope you all having a morning.
Doing cool so far.
That's good. That's good. All right, welcome everyone. I'm going to transition us soon once we get more of us in here. All right, cool. I'm going to go ahead and get us started now. Welcome, y'all. I think I haven't seen y'all since the break, right? Yeah, because I know I saw my other classes yesterday. So welcome. It's been a while, more than a week. Um, let's go ahead and start with a check-in question. Let's see how we're doing. Let's see what today's check-in is. So February 23rd. Okay, so I'd like to know what makes you feel energized, especially when you're feeling tired or something. What makes you feel energized? Let's go ahead and think about it, and then we'll put this into the chat as our morning check-in, and then we'll see who we're missing. Y'all can help me bring some more folks in. All right, I see some things there in the chat. More people coming in. I just want to say this. I like coffee for the taste, but it does not make me awake. Things that make me feel energized during distance learning is getting dressed. So not staying in my pajamas, because if I stay in my pajamas, I'm gonna be lazy. Next thing that would make me feel energized is sometimes taking a morning shower helps wake me up. Sometimes taking a brisk morning walk. Those things do actually wake me up. Oh, and drinking water. But coffee, no, I just love drinking coffee. Let's go ahead and see what you all thought. All right, let's see. Oh, okay. Thank you. All right, we got music. Oh yeah, music. I forgot about that one. That does make you feel energized. We got food. For me, it depends because if I overeat, I get a food coma and I want to sleep. Watching TV, that's awesome. That probably makes me not energized though, but that's awesome. We got food again. Nothing. I just will through it. Okay, that's awesome, Daniel. What is that, AJ? Bobby Shmurda. I don't know what that is, but okay. Makes you feel energized. And we got food, 5 hour energy. Oh, okay. I mean, I would drink those like at the beginning of my teaching, like my first few years. But then I realized I would get a horrible crash after like 1 or 2 hours. It didn't do a 5 hour thing for me. And in addition, I kind of became too dependent on them, so I kind of cut that off. But okay, okay, we got food. Yay! Another one says shower. Same. Yep, water. I agree. Ooh, I agree. I love CJ that you brought in accomplishments. Like thinking about your accomplishments and stuff, that does get you hyped up. I love that. And you also put music and or getting hyped before a game. Awesome. Ooh, Miracle Mate tea from Rob. I've tried teas, yeah. Coffee makes me sleepy. That's so true for me too. I could drink it at night and sleep like a baby. We got coffee. So for some of us, coffee or tea, or I wash my face with cold water. Yeah, that one's good. Coffee makes me feel bad. I drink some today and the pain is coming. It depends. For example, like Pete's coffee, when I used to drink that one, it was like too strong. It has to be at a certain level. But too strong, it does give me headaches. All right, waking up earlier than class because then I have time to fully wake up. Yes, I definitely agree with that. Oh, okay. Rob knows what the Shmo Money dance right now. Okay, so you know what that is? That's awesome. We got soda. That's cool that you all know what that is. That's awesome. I should learn it so I could get some energy. We got meditating. We got yoga. That's a new one. Water and good sleep. Yes, good sleep. Ah, okay. Then we got a challenge to do that dance there on camera. All right. Yeah, these were all some amazing ideas. I also got some ideas from reading. Again, music is a good one. I'm gonna try to energize myself with some music. All right, let's see who we're missing, and then again, y'all can correct me if I'm wrong. But I think I'm missing Miles Ford. I'm also missing Denise. Again, correct me if I'm wrong though. If you're actually here, I'm missing. No, I'm not missing. Carlos. Let's see who else. Am I missing Zion? Zion, are you here? Yeah, I'm missing Zion. Um, and that's it. So that's who I'm missing. Again, if you're friends with these folks, let them know to come on into class, help us out. Um, so again, that's I'm missing Zion. I'm missing Miles Ford. I'm missing Denise. I am missing, and that's it. Yeah, I think. Yeah. And then again, I'll update this. Like double check if we got more people coming in. All right, y'all. I hope you had a relaxing break. Thank you so much for sharing. Awesome. The chat there. That's really funny. Okay. So this is our agenda today, y'all. So we are gonna we have like about a less than a week, about a week maybe left in this module. So we're gonna, go full force, but with grace is what I want to say. Like I definitely want to take our time learning as well. So it's not shouldn't be rushed or anything like that. So today we're gonna be talking about something called instantaneous rate of change. This might be a new word to some of you. For some of you who annotated big ideas packet, you probably saw this and were like, what in the world? Um, Today we're going to be having some credit with Padlet participation. We're going to be on the same Padlet that we were on before we went off into break. We'll see if we get to the Google form. So it does depend on our timing. Asynchronous number 5, our next asynchronous already posted. This one is due tomorrow at midnight. So remember y'all, I'm starting to give like a pushback on the days that things are due. So it's due tomorrow at midnight. So let me know if anyone has questions about our agenda or about the next asynchronous assignment, anything like that, let us know. Oh, yay, we got Zion, y'all. Yay. Welcome, welcome. All right, cool. Let us get a start then, y'all. Let's transition to our new topic. Here's some things I need you to think about in our transition here. We're moving on to looking at speeds and how fast something is going. So here are the 2 essential questions to just think about as we're doing today's new learning. How can I determine how fast an object is going at an exact instance? Like, what does that even mean, exact instance? And I also want you to think about how in the world is slope, like finding the slope of something, connected to speed. These are just the 2 things to think about. And these 2 things that we're thinking about, we're going to be able to answer as we learn more about what these questions are asking us. So take some time to read this. Oh, yes, as a reminder, y'all, you should also take some time to open up your own copy of the slides. So if you kind of remember, we're not taking notes on a piece of paper anymore. You want to open up your own copy of the slides. So, sorry, I muted myself. Let me make sure I remind you all about how to do that, just because it's been a week. So I want to make sure that we all know how to do that. What you do is good. I see AJ's on there. Awesome. What you do is you go to our Google Classroom, and we are on day 7. That's the link that you're going to click on. We're going to go to period 6, and I moved it all the way at the top here, so it's very easy to find. You're going to click on quarter 3, day 7. That's today's notes. And make your own copy, annotate your slide, and follow along with me. So just a reminder, that's how we're following along in this class. Awesome. I got a few handful in there. Let me give a little bit more time just because I just reminded y'all. And yeah, let me also just put that in the chat so we have the directions very clear. Oh yay, we got Miles. Very happy for the attendance in this class. It was really great. Cool. So it looks like we're just missing Denise and Carlos. Is the only 2 that we're missing. Feel free to send them a text. All right, y'all. I hope you all had some time to go and make a copy of your slide. I also hope you had some time to just think about these 2 questions that we're going to think about as we do our lesson. Now I'm going to go ahead and transition us to the next slide, slide number 5. Now, before we actually start to gain any knowledge right now, I want you to think about a ball being thrown, and let's pretend that the ball is being thrown and it has kind of like this projectile motion in the air, like boom, it's thrown and it's moving along like so. Another thing I want to point out is in this graph, the time is in seconds. Down here, you see seconds. And then the height of the ball, let's say it's meters. It's labeled right here. And I want you to think about this question. Imagine you have a ball and you want to figure out how fast it's going. What can we do? And think about this visual. Now, this is going to be Padlet participation. So let me just make sure. So for those of you who are following along, all you got to do is go to the notes section and there's your Padlet. For those who just need me to put it in the chat, I'll gladly do so. Make sure we all have access. Go ahead and you could put your idea there into the Padlet, Daniel, for sure. We could definitely take a look at that. So I put the Padlet there in the chat. We're going to open it up together. Again, have your slides, have your Padlet. You shouldn't close your Padlet. We're going to keep on this Padlet today. And what's cool about this ongoing Padlet, y'all, is you could go back and look at your past learning and your thoughts, which is really cool. But let me go ahead and guide you to where we're at. So you're going to scroll down and we're on column number 10, the opener question. And the opener question more clearly is down here. If you click on the image, imagine you have a ball thrown and you have this graph and you want to figure out how fast the ball is going, like its speed or its velocity. What is something we can do? Just put your ideas. Doesn't have to be right. Just put some ideas on what you think we could do. So I'm going to again put the directions in the chat. We are on column number 10, answering this opener question. All right, I see a few of us there typing. I'm just leaving this up here in case anyone wants to see the question nice and big. Of course, if you're on a laptop, you're able to click it too and make it nice and big for yourself. Again, let's just see some ideas. So if there's a ball that's being thrown, there's meters, there's seconds. What can we do to figure out its speed? So we'll check back in about a minute. I put in there in the chat a bit. So don't forget your name or initial. Make sure you put your name or initial here for your, our daily credit. We'll have, I think, 3 check-ins in this Padlet today. We'll strive for that. Yeah, let me resend the Padlet link for those who need it. I'm going to put it back into the chat. And let me personally send it to anyone who needs it. There you go. All right, I'm gonna go ahead and bring us back so that we could check out what ideas y'all are having. So if we have a graph that looks like that, how can we determine the speed or the velocity of the ball? So we got right here, we got D over T, and I'm assuming we're thinking distance over time, that formula, okay? So we got S or speed equals distance over time. We have V or velocity, distance over time with a question mark. So a lot of you are agreeing on this distance over time. Ooh, we have a new thing here. So we have something like V1 minus V2 over sec. I forgot how the equation goes. Ooh, bringing in some physics knowledge. That's awesome. Ooh, okay, we got to find the slope growth for the distance of 1 sec for the specific time you want. And since the speed changes every second, we probably average out our graph to get an even speed. Wow. So that's an interesting thought process there. And then we have another one where this V minus V1 minus V2 over time of sec. So that's like a physics thing that was mentioned. And then you calculate the distance and time and ticket to get speed. I agree. I love it. So far, everything y'all are saying on point. The ball is moving at a speed of 3. Oh, okay. A calculation 3 meters per second because the ball is at 9 meters at 1, 6 and 2 in the slope. Okay, we're seeing a slope. We're seeing mentioning of physics. We're seeing distance over time. All right. A lot of you are saying distance over time. And then a lot of you know that the distance has to be involved here. All right, look at this. Again, make sure you put your name or initial for your credit here today. Thank you so much. You all are on point. Yes, we are going to be looking at distance over time for speed. Yes, it probably does involve some formula in physics, and yes, it does involve slope. Let's go ahead and talk about this. So notice how you all have that underlying knowledge already, and we're just going to go ahead and solidify that now. So that's right. But what that's going to take us into is this. And we're on slide, I don't know, slide 8, I think. Reviewing average rates of change. So those things that y'all were saying, distance over time or slope, that is average rate of change, if you remember. If you didn't, that's okay. Here's a review. You can find the average rate of change between any 2 points to determine velocity of speed. Again, that's the same thing as saying distance over time, because that's your slope. There's another kind of new definition that we have going on here is that the line that connects these 2 points is something called a secant line. You're going to see this at the end of this. Or, if you're curious, you could check it out on your own slide. But the average rate of change is basically finding the slope between 2 points. So finding the slope between 2 points is going to be distance over time in this case. And it is going to be like that formula y'all were doing with physics. Yeah, I think that's exactly where this is coming from. You guys were doing that subtraction over something. Yeah, I agree. A more simplified way is we could just say it's just the slope. And I know a lot of you mentioned slope. And that's what we're going to do here in this problem. Let's just find the slope. And particularly because we're given these 2 points between 1 second and 2 seconds, we're going to find the speed between 1 and 2 seconds. And then we'll see what that gives us. So let's do that. Let's plug into the formula. First thing we want to do though to use this formula is to label your points. What I mean by that is you always choose one to be x1, y1, and your next set has to be x2, y2. It just always helps. It definitely helps me because I feel like I always like switch numbers in my head or something and I forget, so I have to write it down. So label your points. Next step is let's plug it into the slope formula and then we'll see what we get. So we got y2, that's 6, y1 is 9, so we get 6 minus 9, and then all over, and we're just going to do 2 minus 1. If you were to simplify that, 6 minus 9 gives you negative 3, 2 minus 1 gives you 1. What we then have is a negative divided by a positive is just negative. And we always have to remember, if you're given units, like in this problem, we have meters per second, you want to make sure you include the units in your answer. So in your final answer, include the units. So we have found, in this case, we have found a velocity. We could also find speed here if we make this number positive. So think about like when you're driving a car, we don't say we're going at a negative speed because speed is always positive. So when you're driving a car, we like to talk about it in speeds. But if you're talking about velocity, velocity could be negative. So that's that little note here. So let's read that note. Translation. This is saying that between 1 and 2 seconds, between those 2 points, we are going on average a velocity of negative 3 meters per second. The speed would just be the positive of that number. The speed, if I was to say what's the speed, that's just 3 meters per second. And what you have on your graph right here is that secant line, that definition that I mentioned from before. Like the line that connects any 2 points is called the secant line. And the slope of this secant line is your speed or your velocity. So that's what we just did right here. And you all were on point, right? What you all put in the Padlet, that is what we're doing here. Let's see if anyone has questions about this before we jump into our next check-in. That's okay if you don't, just making sure I'm giving time for questions. All right, awesome. Let's go ahead and now see. Okay, so we just figured out how fast the ball was going between 1 and 2 seconds. That's what we just did in the last slide. Oh, slide 6. But now we want to think about how in the world are we going to go figure out how fast the ball is going at exactly 2 seconds. What do I mean by that? So kind of like think of like when a car is traveling and you want to know exactly after 2 seconds how fast you're going at that point in time, not an average. What will we do then? This is now ideas being thrown out, y'all. So we're going to try to put some ideas and we're going to be on column number 10 in the Padlet. So I'm going to again put the Padlet into the chat. So this is our next check-in. So column number 11. So I want to find out how fast we're going at, or how fast the ball is going at exactly 2 seconds. Padlet is back there, but again, please keep it open so you don't have to reopen it each time. And we are on column number 11. How do we figure out how fast the ball is going at exactly x equals 2 seconds, not between 1 and 2 seconds? So how do we do that? And again, no right or wrong answer right here. You're just going to put down ideas. All right, I put the directions there in the chat. Do not worry about being right or wrong. We're just going to throw out all the ideas that we can. We will have an answer to this, but I first want you to think about this. Like, how can we figure out exactly at 2 seconds? how fast that ball is going. All right, let's have about a minute more here. Put down your thoughts. Any thoughts? Don't worry about it being wrong. Again, make sure you put your name or initial. All right, everyone, let's go ahead and come back. I definitely want to value the time you are taking to think about this first. Before I'm like, hey, this is how we do it. Let's think about it. All right, let's see what y'all said. So we have some inferences that you can count how many points are on the line between 1, 9 and 2, 6. So kind of like partitioning it somehow, narrowing it down a bit. If I remember, you can use slope to help you find the speed of car at 2 seconds. Okay, so thinking that slope is still going to be involved. Awesome. Then we have, what if you just do 2 divided by 2 seconds? That's an idea. You can find the slope slash create a small slope near the exact point at x equals 2. Interesting. Using a smaller slope is. You can see what the point of the ball is going and base it off the slope. You can see the speed. Okay, so using your graph there to kind of make an estimate. Then we have, you could do 6 divided by 2, which is 3 meters per second squared. Yeah, which is very similar to what we did before, right? In that slide 6, I believe. And then maybe plugging into an equation, maybe using a table. I like those ideas. Wow, those are really, really good. I think we could look at the number it started on and the end number and see how long it took between there to get to the end. Wow, this is so great. Wow, these are awesome. Maybe when you find the slope near the point of x equals 2. So another mention of that. I know someone else mentioned that too. You can use the slope to help you find and if you're probably still writing, that's okay. Okay, so do make sure that you finish your thoughts here, again, with your name or initial here for our credit today. Let's figure out how in calculus do people do this? How do they find out how fast something is going at an exact point in time. Let's think about this. We're going to go to slide number 8, everybody, on our slide. So we're back on the slide, slide number 8. Now, this instant or exact speed at some point in time is actually called something. It's a long word, instantaneous rate of change. So remember the thing we just did before, that's called average rate of change. This is called instantaneous rate of change. Now, I'd like you to think about this. The best relation I can make this to is when you're looking at the speedometer on a car. Like either your parents or if you drive, right? If you have your permit, or sorry, not permit, if you have your driver's license and you're driving, whatever. But everyone's familiar with this speedometer, right? So when you're driving a car, the speed you see on the speedometer, do you all think this is an instant or is it an average speed? Is it telling you how fast you're going at that moment? Or is it telling you on an average how fast you're going? For this one, go ahead and use the chat. We're not going to use Padlet. So use the chat here to answer this here question if you're ready to. If you're not, just think about it. What do you think is happening here? And let's see what we get. All right, we have 2 that say average there. And then, so 3 who are saying they think it's like an average. We have someone saying instant question mark. And then remember, average would mean that it's telling you after every so minutes or something, like how fast you're going over a certain amount of minutes. So we have average and instant, okay? Let's see if there's any other ideas or if anyone wants to add a because or anything like that. I just want to give everyone time to think about this and then we'll see what the answer is here. All right, cool. So we have a majority kind of leaning towards average. I would like to know why, Sam, you thought instant question mark, but it's okay if not. Okay. Oh, okay. Bye, Rob. Rob. Okay. So let's talk about it. So let me give you the answer. So the speed that you see on the speedometer is actually your instant speed, everyone. So I know a lot of you said average. It would be an average if it was like perhaps telling you after 1 minute or so, like, oh, this is your speed between the first minute you were driving. This is the speed the second minute you were driving. But don't you notice, y'all, like when you're driving, that speedometer, that thing, that red thing is constantly moving. It's adjusting like how fast you're going in that moment, actually. So this is actually called an instant speed. So think about that. Think about how fast that I wouldn't know what that red thing is called. It's like that. If someone thinks of a word, let me know. But that is constantly moving. So within a minute, right? I could do a variety of speeds. Within a minute, I could speed at 100 miles per hour, and then I could slow down 5 miles per hour, speed up, slow down. I could do a lot of things within 1 minute, and my instant speed would be very different throughout that time. So the speedometer is telling us an instant speed. So that is super important. So average would have been if it was like after a certain amount of time, it would tell us, hey, on average between these 2 periods of time, you're going this fast. But what we're actually seeing is the instant speed. So let's think about that. Let me see if anyone has questions about that though, on why it's actually going to be our instant speed that we're looking at. Okay, awesome. Let's go ahead and transition. So just making sure if there's questions about why this is an instant. Again, the best reasoning I could give is like while you're driving, when you like push down on the gas, you're gonna see that instantly that red thing goes up. Your speed is going up and it's telling you at that instant how fast you're going. It's not gonna give you an average. It's not gonna go, your car isn't sitting down and on a calculator and calculating these average speeds, it's actually telling you at that instant how fast you're going. So then what does this relate, right? So overall, the instantaneous rate of change, first off, the instant rate of change or the instantaneous rate of change, they mean the same thing, is when you determine the rate of change at an exact instance. So that speedometer thing in your car, that's an instant rate of change. And that's when we're trying to determine our speed or velocity, whatever, at an exact point in time, at that instance. So that's an important definition of what an instant rate of change is. Next one is, well, how do we do this? You all put a bunch of different ideas right now on the Padlet. This is the process that we're going to be doing. This is the process in the big ideas packet. Some of you did mention this process about making the slope smaller, but we're not making the slope smaller. We're going to be estimating the instant rate of change by moving one point closer to what we call the point of interest, or whatever point we're interested in. And the last problem we're interested in at 2 seconds. So you're going to see visually what I mean by this once we do this, but this is the process. We're going to move one point closer to the other point, and then you're going to calculate the slope of those two very close points to get an estimate of your instant rate of change. And maybe, I don't know if choosing 2 points that are very, very close together, I wonder if that reminds anyone of a past big idea. I know it's been more than a week, but feel free to share. Does remind you of anything in the chat or not? It's okay. I'll just give some time, or think about if this reminds you of anything. When we're making points really, really close, I wonder if that reminds someone of a past big idea. Oh, let's see. I forgot its name though. It's the getting closer thing. So Danny, you're right. It is the getting closer thing. I wonder if anyone remembers the name. But you're right. It is the getting closer thing. We have a formal name for it. Starts with an L. Maybe
Limits?
yeah, think of the Mean Girls movie. Remember the limit does not exist. Well, in this case, the limit will exist. But yeah, the thing about like making 2 points or anything get closer and closer or approach something, that's limits. So this is actually us. We're going to be applying that big idea of limits. So I put it down here too. The process of moving 2 points closer and closer together, that is us applying our big idea of limits, everyone. So that's actually why this is even at all related to what we were doing before we hit the break. So we're continuing that. See how it's all kind of interrelated. So it shouldn't just be me teaching you random stuff. It all has a storyline that it's leading up to something. So yeah, just think about that. This is just important to read and be prepared for what we're going to do next. So our goal now, we're still going to be looking at that ball problem again. But this time we're going to try to find the instant speed at 2 seconds. How fast is it going exactly at that time? And again, we're going to be doing the process of this second bullet point. We're going to estimate it by moving that other point closer to it. Let's do it. All right, y'all. Example 2. And I went ahead and we're on slide, I don't know what slide this, slide 10. We're on slide 10, everyone, example 2. Here is the strategy up here. We're trying to figure out how fast the ball is going at exactly 2 seconds. So we're moving that green point. Remember the green point? It was at 1,9. We're moving it now closer to 2, very close to 2. Take a look at my picture. I just basically went on Desmos and I moved that green point very close to 2. Instead of X being 1 seconds, I made it 1.9. Notice how 1.9 is very close to 2. That's why I chose that point. So now I have 2 very close points, and we're going to go ahead and try to find the slope of this. The slope of that is going to give me a better estimate of the instant rate of change at exactly 2 seconds. So let's do it. Step 1 is I'm going to, because I know I'm going to be using the slope formula, I'm going to start to label it. So I'm going to do x1, y1. And then we got x2, y2. And we're going to just go and do our handy dandy slope formula. Here it is, y2 minus y1 all over x2 minus x1. We just got to plug in and subtract. So according to these new coordinates, I'm gonna do 6 minus 6.75 on top, divided by 2 minus 1.9. You're gonna need a calculator. I definitely did. I used my phone. So this is what I got when I subtracted the top numbers, and then the bottom I got 0.1. I went ahead and divided these two numbers to see what we get. And I got that my slope or my speed or my velocity here was negative 7.5 meters per second. So remember previously what we got, I think -3. Now we got negative 7.5 when I moved the points closer. So right now we're getting a better estimate of how fast we're actually going at x equals 2 seconds. Notice that we're going faster than between 1 and 2 seconds. So think about that. So that's what we got so far. Oops. And let's see, does anyone have any questions of what we just did here? I'm going to pause and make sure you have your questions addressed. You could ask me privately or openly, whichever way. All right. So, okay, cool. We got a pretty good estimate here, but guess what? We could do even better. What if I move this second point even closer to 2? What am I going to get? Because, hey, you could always keep getting closer and closer. Remember when we were doing limits? That's what we're doing when we're creating our tables. And it's okay if you don't remember, but let's just choose a point that's even closer. Now in this picture, I chose the second point to be even closer. I chose 1.98 comma 6.158. And again, I just used decimals. I clicked it and it gave me the point. So now we're moving the 2 points even closer to each other. I'm keeping the second point just flat. It's just there. The green point is the one that's moving closer though. So now let's go ahead and find the slope between these 2 points. So again, the process is going to be the same. I'm just going to do x1, y1, and the second one's x2, y2. And we're going to go ahead and find the slope of these two and see what we get now. Let's see if it's even better approximation of how fast we're actually going at x equals 2 seconds. So again, the process is the same. I'm going to substitute my values, and then I'm going to subtract them using a calculator. You're going to get these long decimal looking things, right? When you're doing approximations. That's okay. That's part of it. We're going to divide this and we're going to get, look at this. So our slope now, or our velocity now of the ball, is going to be negative 7.9 meters per second. So notice how it's getting even closer and closer to a certain number actually. All right. And I also want you to notice this line, this red line that I keep drawing on here. That's the secant line. Notice how it's changing too. I'm going to be asking you all a question about that in a second, of how that's shifting as our points are moving closer and closer. Okay, so Danny, you said it looks like the slope is approaching -8. So first it was -3, then it was -7.5. Then we moved the points even closer. We got -7.9. I mean, I would agree. Hey, if we did even closer, I feel like we'd be getting closer and closer to -8 meters per second. So I like that you're already thinking about like what it's approaching, which is the limit. That's awesome. All right, let's see. Does anyone have any questions about this calculation and what we did here? Okay, so this is how you approximate instant rate of change. This is what you'll be doing in your mini final once we hit that. So just keep this, it's super important, this lesson, this process of approximation and moving 2 points closer, you're gonna be doing that. But don't worry, you're gonna have group time as well as, on your own to process this. Okay, y'all. So we just went through these examples of how to approximate instant rate of change. Now I have a question for you back on the Padlet. And let me get you the Padlet once again in case you closed it up. And we're going to be on column number 12. And the question is about that red secant line. So let me just put this into the chat. Put the Padlet back in. We're going to be on column number 12. Sorry if I said 11. Column number 12. So the question is posted right there. It says, what happens to the secant line? That's the red line. That's the line that connects the 2 points. When the 2 points are getting moved closer and closer to each other. And I also asked, how is what we're doing right now related to limits? And I know, Danny, you already kind of shared some of your views. Feel free to like kind of rephrase that if you understood what Danny said, or put down your own understanding. You could also be honest and be like, I really don't know how this is related to limits. That's okay. Again, anything is, is valid here. So again, the first part of the question is, what is happening to this red line as the 2 points are getting moved closer and closer to each other? What is happening to that line? How is the slope of the line changing? The next thing you want to think about is, how are limits at all related to what we're just doing right now when we're trying to estimate the instant rate of change? Let me put the directions once more in the chat so we all know what we're doing. We're on column number 12 on the Padlet. And the question is right there on the Padlet. I'll give you all a minute there. Again, don't forget to put your name or initial. Again, any thought or any contribution on the Padlet is completely valid. And then we'll talk about what we see. All right, y'all. I'm interested to see what y'all are thinking. So, as the 2 points are moving closer and closer, first pay attention to what we're doing. We're moving these 2 points closer and closer because we're trying to find the instant rate of change, or another way to say that is how fast the ball is going at exactly 2 seconds. So, in this diagram or in this picture, screenshots of the different calculations we did, we first started out calculating the speed between 1 and 2 seconds, and we got -3 meters per second. Then I moved this green point even closer to the 2,6 point, and I got an even better estimate because, again, the closer the points, the more close you're to determining the instant speed or the instantaneous speed. Then I went even closer, and then we got a slope of -7.9 meters per second. Again, that's going to be velocity. And I asked you, like, how is that secant line, that red line, changing? And as well as how in the world is this at all related to limits? Let's think about what y'all said. So we have, as the 2 points are getting closer and closer, the secant line takes a closer angle to that of the graph. So it's kind of like, I guess I could see like it's more angled, like it gets more angled. I could see that happening. When the 2 points get closer and closer, the secant line starts to move closer to the actual slope of the graph. Wow, that's really cool. Yeah, that is actually very powerful. I love that one. That is exactly what we're doing. So as the 2 points are getting closer and closer, the line is almost like becoming the exact slope of what's happening near that area of the graph. That is amazing. I love that one. Yes. When the 2 points get closer together, the slope of the line seems more similar to the actual slope of the graph. Yeah, that's similar to what was said prior. That, yeah, I think these two are saying the similar things. Amazing. The line is getting steeper. Yeah, that was mentioned. So I agree. So over time, as the points are moving closer and closer, the line is indeed getting steeper, right? I see that too. All right, the line gets steeper and steeper, and the 2 points get closer, and it looks more like the graph. Yes, that is, y'all are hitting the main points. Y'all are seeing the main essence of what's happening here. And then, yeah, so another way to say the line getting more steeper, I like this wording, the line gets more and more vertical, meaning the points are getting closer and closer together. That's another way to think of it, the 2 points or the line getting steeper. Ooh, okay. So this is an attempt to bring in limits, which I love. 2 points move closer to the points, going further down, making them have a limit that is a similar distance. We have it becomes vertical. We got more vertical mentions. And then we have that the secant line becomes more direct to the slope, and the line is decreasing as the slope is getting smaller. Yes. Y'all, this is really, really great. Again, this is what we're going to be doing to answer part of our mini final once we hit there. I think I already posted it though, so y'all are free to take a look at it, but we're not going to talk about it yet until we hit there. So we'll get to that. All right, y'all. So let's see. We're not going to be doing the checkout form. So we're going to have to continue this tomorrow in our next class, y'all. I don't have a checkout because I thought our checkout was going to be Google form. So our checkout is to just think about what we learned today and, give yourself a pat on the back and have a good lunch, y'all. All right, y'all. Have a great lunch.
Hi, Danny.
Bye. Bye, Danny. Bye, CJ. Bye,
Okay,
y'all.
see ya.
Bye. See ya. See you tomorrow.